We have already seen in the last example, in the last video, about new kind of setup, two-factor setup, and we shall continue with the analysis of that using a computer. But before that, I will spend this video to understand something which is much more generally applicable other than simply two-factor models and something that really brings to the fore the statistical aspect of linear statistical models. It is not just about doing some linear algebra and learning some computer syntax. So what is the statistics involved in it? And there are four basic principles of statistics that we have to use here, that we have been using, but I just want to make them clear. And these four things are called: number one, the concept of control; number two, the concept of confounding; number three, the concept of blocking; and number four, the concept of randomization. The first concept, namely the concept of control, is this. Whenever you have a black box system, you have some input and you have some output, and you want to see whether the input has any influence on the output, always make sure that you are comparing one level of the input with another. Do not just say that I have put some input and I have got some output, so whenever I will put this input, I will get that output. That is not necessarily true. So the input is causing the output, or it is the input which accounts for the change in that output. You cannot make such a statement. Let's take a very simple example. Suppose I take some medicine. Say I am ill, and I take some medicine and I get well in 1 week. And I say, you see, the medicine worked wonder. I just became well in 1 week. You can't say that. You can say that only when you compare it with someone who has a similar illness and did not take the medicine. It's quite possible that that guy also became well within the same period of time. So in that case, your medicine had actually no effect. It is possible that that other guy got well within 2 days, while you, under your medication, took 7 days. So in that case, your medication is actually something which is bad. So that is why I am saying that whenever you want to say that some input has an effect on the output, make sure you compare it with a benchmark value. Now here is sort of a humorous way of remembering it. Suppose you go to a room and you find that there are two switches. One is the on position and the other is the off position. And you find that there is also a bulb, a light bulb, which is on. And based on that, you want to guess whether which switch is actually controlling that light bulb. Now you just look at it, you see this switch is on, this switch is off, so you immediately conclude that this must be the switch that controls it. So what you do is that you try to turn this light off, so you flick this switch off. And you find that the light does not go off. It remains on. You immediately understand that this switch is really not controlling it at all. Now you try this one. This looked like off, so you flick this fellow and immediately the light goes off. So now you understand that actually this switch was controlling the light. Now, why did you arrive at the wrong conclusion when you just looked at the two switches without touching them? Because you compared the value of the switch on, originally it was on, and the value of the light. They were both on. So you thought that since this is on and that is on, this on is causing that on. But when you changed it, that is, you compared how the output behaves when you are flicking it. So you are comparing its on position with its off position and looked at how the output changed. Then you got a much better idea about the input-output relation. So do not compare value of the input with value of the output, but compare the change of the input with change of the output, that is a much more reasonable way of coming to a conclusion. Now, in various studies, you need to do that. You must set a benchmark and see if I change the input from the benchmark to a new value, how things change. Say, for example, you are interested in finding whether a particular medicine has got any effectiveness in curing some kind of disease. Then do not just say, here I took a bunch of people, I applied the medicine to them and they got well, or 80% of them got well. That's not enough. You must start with two groups of people who are more or less identical, have same kind of disease, and then you should take these two groups of people, and for one group you will apply the medicine, and for the other you will not apply the medicine. Compare how these two groups differ in terms of their getting well. Now, sometimes it so happens that you give the medicine to one group and not to the other group. Now, the group that gets the medicine has a feel-good factor. We have got a medicine, so we are going to get well soon, and this feel-good effect sometimes helps them to get well better. It is not really the chemical effect of the medicine. In order to get rid of this, so that we can really understand what is the effect, the true chemical effect of the medicine, what we do is that we give to this other group, that is often called the control group, that is the benchmark group with respect to which you are comparing, that is the group to which you have not given any medicine. What you do is that you give them some medicine. That's something that just looks like the real tablet, but it does not have that chemical in it. And this is called placebo. So you give placebo to the control group, something that looks like the medicine, so the patients do not really know that they are not given the true medicine, but you, the researcher, know. And this is called a blind experiment, because the patients are kept in the dark as to whether they have got the real medicine or not. Everyone sees that they are getting identical looking pills which they take, and the medication, the true medication or this placebo medication, continues for say a month, and then diagnostic measurements are made. But the researcher knows that some people are actually not getting the true medicine. Now we can compare. So the group which you are using as a benchmark, that is called the control group. And you can never apply linear models meaningfully unless you have a control group. So the linear algebra doesn't care about that. It just cares about y equal to x beta plus epsilon. The computer does not care about that as long as you can write a suitable formula in LM. But the statistics will become meaningless unless you have a control group to compare the thing against. And I talked about the blind experiment where the patients are kept in the dark as to whether they have got the true medicine or the placebo. There is another version which is called double blind experiment, where the experimenter is also kept in the dark, so that when he or she is taking the diagnostic measurement, he is not getting biased as to, I know this fellow has got a placebo, so I know that he cannot get well. So everything is kept in the dark, but the true identities are written down somewhere, possibly generated randomly using a computer and kept in a secure place. So after all this data has been collected, then that file is opened, and now we know who is placebo and who is the true medication. So that is called a double blind experiment. It is blind on part of the patient, it is blind also on part of the doctor.